Hello and welcome everybody. Thank you for joining us for today's webinar, Ensuring Excellence in Space, Element's Advanced Product Quality Testing. Presented by Element Materials Technology, I'm Michael Kuhl and I'll be your moderator for today's session. As we look forward to the future of space exploration, where every mission pushes the limits of technology and endurance, the need for rigorous high-performance testing is more important than ever. In space, there's no margin for error. Every component must withstand intense launch conditions, vacuum exposure, radiation, and extreme thermal cycling, all while maintaining peak performance for years in orbit. At Element, we help customers meet these challenges head-on through comprehensive product qualification, testing, and materials testing. Our global network of laboratories supports spacecraft and satellite programs from prototype through launch, helping teams reduce risk, improve reliability, and ensure mission success. Today's session will explore how we apply our comprehensive testing capabilities to validate next-generation space technologies. You'll hear insights on radiation and thermal cycling testing, fatigue and fracture toughness evaluations, EMI, EMC, as well as NDT and various other techniques of materials testing that we have available, and of course are needed by these next-generation platforms. We're proud to be joined by three of Element's most respected technical leaders, each with deep experience in aerospace testing and engineering. We have Eric, our Senior Applications Engineer at Element LAX. He has over 38 years of experience in aerospace, military, and commercial testing. From dynamics to fire to space simulation, Eric brings a practical, solutions-oriented approach that helps customers navigate complex validation programs with confidence. We also have Justin, our Director of Non-Destructive Testing for the Americas. He has spent more than 2 decades developing advanced inspection practices across nuclear, oil and gas, and the aerospace sectors. From phased array imaging to automated submersible inspections, Justin's innovations in NDT are reshaping how we ensure structural liability. We also have Frank joining us as well, Technical Directors of Metals Testing at Element Huntington Beach. He's been with the organization since 1997 with expertise in fatigue, fracture mechanics, materials characterization, and chemistry. Frank provides customers with high integrity solutions for critical aerospace materials and components. Each of these experts brings a unique lens to today's topic, and we're excited to share their knowledge with you. Just a few quick reminders before we get started. Please feel free to submit questions at any time using the Q&A panel on your screen, as well as, of course, the chat box that's available to you. We will also have and push aside time for Q&A at the end. Also, a recording of today's session will be emailed to all registrants after the event, with a posting of this session on YouTube happening Monday. With that, thank you again for joining us, and let's get started. You have the microphone, Eric.
Well, Mike, thank you for the kind introduction. Frank, Justin, it's nice meeting you. I'm excited to hear about NDT services and understanding more about your capabilities. I'd like to welcome everyone here today joining us for this webinar. My name is Eric Fernandez. I'm an applications engineer for the Element LAX division, and I'm here to provide an overview of PQT services. PQT stands for Product Qualification Testing. The PQT group is relatively new to the Element organization. Our group primarily is made up of the acquired NTS and Wiley facilities that specialize in certification and validation of commercial, military, and aerospace equipment. We provide a wide range of testing services, including precision cleaning, space simulation, environmental, proof, burst, and dynamics testing. I'm looking forward to working with you and the NDT group to see how our areas of expertise complement each other and how we can integrate our service offerings to support the aerospace industry. Justin, can you take time to provide some insight into the non-destructive testing, NDT, side of the business and provide an overview of these services?
Absolutely. So, some of you might be familiar with NDT, others not so much. What is NDT and why do we need it? Well, defects or flaws in components can significantly impact the mechanical properties and overall performance of the final product. As a result, it's essential to continually refine our inspection process and implement robust methods to increase the odds of defect detection and ensure reliability of the incoming products. Failing to identify these and address flaws in the manufacturing process can have severe consequences, especially when we're manufacturing for safety critical applications I've personally seen improper selection of NDT methods lead to catastrophic failure, reduction in lifespan of components, and operational inefficiencies leading to increased rework, which obviously is never a good thing. When we talk about the different types of NDT methods, we predominantly segregate these into two categories: surface or slightly subsurface, such as eddy current, penetrant, and magnetic particle, and then predominantly subsurface or volumetric inspection, such as ultrasound, or radiography. In regards to ultrasonic testing, this is probably one of the biggest methods that we specialize here in Element. So you're doing a volumetric inspection of components, and there's a multitude of reasons that this is typically one of our go-tos. Aside from the fact that we have data retention, as you see in the upper right-hand screen here, that's a planar C-scan image of a component where we have 3 areas of disk bonding. So the good thing about this is that we've got this record on file that we can share with the engineering organization of the customer. And one of the good things about fully automated UT is it's an image similar to a map that's easy to absorb for someone that may not be familiar with the ins and outs of ultrasound. In addition to that, immersion UT is one of the areas we specialize in. As you can see in the lower right-hand image, that's one of our fully automated immersion disk tanks. And the benefit here is that using the water as a wedge, we can create a multitude of angles very quickly on a multitude of surface configurations: flat, profile, curved, bores, etc. And we can induce angles very rapidly and repeatable. So this works well for routine high volume components and bespoke one-off orders we get in from customers. Now, obviously we can do contact testing, but because of the increasing complexity and near net shape of a lot of the components we're getting in the space industry and aerospace as well, the near surface resolution and the ability to set up for repeatable inspection is key, which is why we tended to go towards automation and immersion in regards to UT testing. Obviously, components ranging from 1 inch in diameter to 20 foot long. It really depends on the end use and configuration, but having these automated steps has allowed us to encompass all of this in one system repeatably and reliably. RT or radiographic inspection is another volumetric process that is very beneficial and similar to UT. You know, if you've ever been to a doctor's office and gotten an x-ray, that image of what's happening subsurface on your component is pretty readily absorbable to an engineering associate, right? We can see we have some voids in this weld in the upper left-hand corner. Another thing that radiographic inspection has lent itself to, specifically in space applications, is additive manufacturing. So with additive manufacturing, obviously a pro there is you get near net shape. It's close to finished form as you can get with minimal machining and input afterwards. With that, due to surface configuration and the complexity of some of these shapes, CT or digital radiography has been a huge tool in allowing us to rapidly inspect these components and then have digital information that we can review at any point in time and share with the customer. As you can see in the upper right-hand corner, obviously these near net shapes or these very complex finished machine components would be very difficult to inspect with ultrasound inspection because of the configuration, which is why we see pretty much a 50-50 split in the industry, depending on whether the customer is opting for radiographic inspection versus UT inspection. Eddy current testing is not so much a volumetric inspection, but a surface-related inspection we do. Typically, we can go slightly subsurface, down to 1 or 2/10 of an inch of material. But again, here, this is fully automated. We have data retention, so we can share this image with the customer for review. The customer can even have licensing of our software to pull real-time data up and reevaluate what was inspected on our components. So while it is limited to surface inspection and you can't go very deep on the component, we've typically in the industry seen a shift away from PT towards eddy current when you want a high amount of data that you can accurately and repeatably review with the customers. We've got contact, handheld, fully automated systems across our locations in the United States and in Europe. that can do all of these inspections on a variety of surfaces, not necessarily just flat, looking for planar defects or defects oriented in radius or complex machine surfaces. Penetrant inspection is another surface inspection, which again, typically when the customer is working with us to tailor a technique or multiple methods for optimal defect recognition, penetrant has always been the go-to in the industry. The downside to this is historically you haven't had any record other than the operator inspecting the component looking for said defect. However, we're working with the new technology now where we can actually take videos and real-time photos for assisted defect recognition on penetrant testing, where these camera systems will actually lock onto the fluorescent that's being produced by the indication, as you see in the lower image here, and you have a permanent record that can be reviewed later on in time, again, with the customer. Configurations can vary greatly in penetrant testing. Here we have one of our fully automated lines that can inspect thousands of components on a daily basis. But then also we can set this up for bespoke 1-2 piece orders. And the good thing about penetrant testing, as I'm sure you're aware if you're familiar with NDT, is that surface condition isn't as impactful as it is in, say, UT with the outcome of the inspection. Magnetic particle testing, if I'm being honest, in space applications, becoming less and less frequent just because it is primarily limited to ferrous materials that can be magnetized. And so MT inspection inducing a magnetic field looking for surface breaking defects or slightly subsurface is often being replaced by penetrant testing or eddy current testing for surface or near surface defects. Yet we still have the capability to inspect a variety of configurations across the industry. And again, here we can see components being inspected in cylindrical forms, plate forms, etc. The good thing about MT testing is that can be highly portable, similar to PT, on-site, off-site, etc. So NDT in your program, obviously we have a lot of specification-driven inspection in the industry. I see a lot of customers come to us and say, I need X, Y, and Z done in NDT because the specification dictates. But there are also customers that come to us with R&D driven solutions. I had a customer, if you see, this is a rotor with a brazed surface on it. And they came to us and said, hey, we have a problem. Here is a defective rotor. We have a lack of brazing. We want you to come up with a technique to inspect this so that we're not wasting all the subsequent time in machining and processing of said rotor. So we developed a fully automated immersion inspection on the rotor. And this is a 3D image. If I could rotate it in the image, I would. But we did a 3D overlay of the brazing surfaces of that rotor, and we identified areas where we had a lack of bond there. And that was done upstream in the manufacturing process. That's a situation where the customer came to us and said, we have a problem. Here is the problem. We want you to engineer a solution to us, for us, not so much spec driven. We also have complementing NDT surfaces for DT. We had customers looking for hydrogen-induced cracking, and they were putting these in an H2S solution, and rather than just section them endlessly in 2 millimeter EDMs, looking for the flaw, we developed a technique with UT to scan the samples pre and post exposure so that we mitigated the amount of sections the customer would have to do blindly looking for where the hydrogen-induced cracking would be located. So that's a complementing service that we put together to work with a gentleman like Frank and Eric on the DT side. So obviously there's a lot of spec-driven NDT, but we're more than competent and capable, and I love working on these R&D projects to engineer solutions for the customer that aren't blatantly obvious in some situations.
All right, thank you, Justin. All right, hi, hello everyone. Thank you for joining us. My name is Frank Nguyen. I've been with Element 28 years, and I'm on the destructive side. As you know, every day across Element, we perform thousands of destructive testing. But most important for space is fatigue, crack growth, and fracture toughness, as it can determine which component is used for what, and also the lifespan of the component, but also how we can prevent failure, which I will go into further details after this slide. So Eric, you want to talk about low oxygen thermal?
Sure. Thank you, Frank. Low oxygen thermal cycling is something we specialize in. We have developed systems to quickly cycle components designed for space to simulate LEO and MEO orbit temperatures. Having components tested in a low oxygen environment helps alleviate false failures caused by moisture not representative of space. This testing can help ensure the longevity and durability of space hardware. We also perform thermal vacuum testing to simulate pressure and temperature extremes encountered in space, along with vacuum bakeout to help remove dangerous material like moisture, hydrocarbons, and other gases that can be released in the space environment, potentially impacting sensitive equipment. We provide precision cleaning, inspection, and post-bagging services. Contaminants can cause corrosion, fractures, or even explosions in hydrogen or oxygen-rich environments. These services are critical for propellant tanks, oxygen, and hydrogen lines. The PQT group has many locations for EMI and EMC testing to ensure electronic devices can operate correctly in their intended environment without causing or being affected by electromagnetic interference. We do this by superimposing a signal onto the electronic device to ensure it doesn't affect its performance. Then we measure what the device emits to verify it's within safe limits. Another service to mention is our dynamics department, which supports vibration, shock, and acceleration testing. It looks like we're ready for our first polling question.
Yeah.
This looks to be related to the NDT side of the business. Cracking growth rate is faster at elevated temperature, true or false? Frank, this sounds like a question that came from the world of fatigue, tensile, and stress testing. Would you like to provide some insight?
That's correct. I think we're going to take the poll first. Let's see here. We'll wait a minute until we get all the polls in. All right. Great. I think we have a lot of smart people in the audience here. It is true at 75%. So I'm going to go into details of, here's an example of our aluminum 2024 that we did testing in cryogenic, which is minus 320 degree, and then also at room temp. So in fatigue crack growth, usually you measure at the perisection, which is very, at the point where it's linear, the most linear part and very predictable. As you can see here, in cryogenic, it's actually at half the rate at room temp. So if you imagine cold temperature, it actually slowed down the electron. So it actually helped the crack growth rate to slower at a much slower rate than at room temp. So this is in aluminum. And then if you go on to similarly for titanium, and then you go from room temp to elevated, at 347 degrees Fahrenheit, you're actually seeing the growth rate is actually 4 times at room temp. So definitely temperature has a lot of effect on the crack growth rate. So by understanding the crack growth rate, if you imagine a spacecraft, right, with we are traveling in space, and every time you turn on the engine, you get elevated. And then if you're just gliding through space, and Elon's talking about going to Mars, imagine how low the temperature could get. So if we understand the rate of the crack growth, we can actually predict the lifespan of certain components under cyclic load. So here's what we do. Here are some examples of what we do at HB. For fatigue crack growth, there are two methods, which is we use the clip gauge or COD. It measures the crack opening, or we can do the direct current potential drop, meaning you have a current that flow across the sample, and as the crack growth, you will see the current drop. So you can actually monitor the crack growth as it goes with the potential drop, which mostly commonly that we use at HB. All right, and then here's another polling question. Which alloy exhibits better crack growth resistance? Is it aluminum or titanium? All right, 80%, awesome. Which is correct. So one of the reasons why I chose to talk about titanium and aluminum is because these two alloys are the most useful on aircraft and also space. With titanium, as you can see here, this is in fracture toughness, and you can see that the final stress intensity is literally almost double what we use in aluminum, and also the load stress. So titanium is actually a better alloy for fracture toughness and fatigue crack growth resistance. As you can see that it's much more higher strength, it's ductile, and it's low resistant to stress corrosion. So titanium is often used in rotating parts like fan blades, while aluminum, for its lighter characteristics, are often used in fuselage, in non-rotating part, but also titanium is used, for example, in landing gear as well because of its higher strength. And fracture toughness in K1C and also fracture toughness in J1C, and I'll also understand fatigue crack growth. So fatigue crack growth is understanding how the crack growth is propagated with different alloys, and understand the whole from the initial crack to the final fracture, while fracture toughness is actually identifying which metals, as the term goes, fracture toughness. So is to understand which alloy like titanium and aluminum can withstand fracture. Here's an example of a titanium sample. This is what we call a CT specimen. Compact tension, where we have a notch right in the middle, and the two round slots right there. W3 means 3 inches, so it's a measurement from the center of the round spot to the other side, so that's 3 inches. So we can work from W1 to W5, so meaning from 1 inch to 5 inches. And here's how we would load it into our frame. We have the 2 bolt right there just to do a cyclic load. So first we do a pre-crack, and then we do a cyclic loading. It depends on the material, on the specification, how much load, and what is the frequency to apply to it. And then we just apply a static load, and it continue to pull. surprisingly, even though aluminum is lower in fracture toughness, but it takes longer to pull apart, while titanium is stronger in fracture toughness, but it's very brittle, so it breaks faster. So here's what it looks like afterward. And from here, we can actually examine the breakage. We can use our metallurgical lab. We can look for all kinds of different, like porosity and other characteristic into the breakage. So similar to fracture toughness, which we perform, or K1C, we perform to ASTM E399. It's from plane to elasticity. So what does that mean in our language? So you can measure, for example, if you look at a rubber band, from elasticity to yield. So if you keep pushing and pull on the rubber band, when you take the load off, it actually go back to normal, and there's no deformation. But in 1820, which is J1C, we actually go from elastic to plastic fracture. So we're going beyond after that stretch. So E1820 is very good for determining the damage tolerance design. So as space travel continues, you can kind of predict the behavior of certain component at yield and what happened after yield. So titanium by far is the best for, like as I mentioned earlier, for component for rotating part, or components that are exposed to extreme heat, like extreme cold and also elevated temperature. And that's the difference between aluminum and titanium that we test daily. And so our next testing right now, this is a vacuum chamber. Of course, we're trying to simulate space. In the next couple of months, we are gonna start proceeding testing fatigue crack growth, fracture toughness, and other testing like tensile in a vacuum chamber, where we can actually have a heat exchanger in here that can go up to 1400 F, and also as low as 320 by pumping in liquid nitrogen. Our goal eventually after this is going to liquid helium, which we can go down to minus 500 F. So it's going to be an exciting time to learn to get all these new data that can simulate space. All right, so here we are. Why choose Element? Because we have a variety of different testing. With the acquisition of NTS and Eric expertise, we're now open up to a different variety of environmental and other testing that we were not able to do before in Element. Eric, can you shed some light on? I think you're on mute, Eric.
Sorry about that. Yeah, I can help shine some light on these disciplines. We perform acoustics testing using large reverb chambers that produce sound waves to simulate launch conditions to verify components can withstand the extreme sound pressure levels generated during launch. This is to ensure the vehicle systems and electronics function correctly under launch and flight conditions. We provide a wide range of environmental services, including sand and dust, salt fog, solar radiation, temperature, humidity, altitude, explosive atmosphere, and explosive decompression testing. These services are covered in MIL Standard 810, MIL Standard 202, MIL Standard 883, MIL Standard 331, and RTCA DO-160, just to name a few.
Well, with that as well, I think really it's the key thing with any sort of harsh space environments is Element is uniquely positioned for that environment for these testing programs and complementary testing or not complementary, but comprehensive. That's a better word. Comprehensive testing programs in order to really span the entire development cycle. So with that, really, we develop multiple CapEx expenditures to really grow with our customers and really support their programs from that end-to-end perspective. So Eric, could you talk a little bit more about ASTM, outgassing testing, acoustic noise testing, any of the environmental testing programs that we have going on, specifically within LAX? And I think your knowledge expands beyond LAX as well in relation to product quality testing.
Yeah, I think I kind of touched on some of those types of services. The ASTM E595 is really a materials type test where we'll take a material sample in a vacuum environment and do an outgassing measurement where we can check for total mass loss, CVCM, and water vapor regained. That service is more on the military, the materials type side of the business. We don't really do that at LAX, but we do a lot of testing with, the outgassing where we're measuring TQCM measurements to measure the overall outgassing environment. We do a lot of precision cleaning and yeah.
Ooh, could you tell us a little bit more about precision cleaning? I've been seeing that a lot on my side as well.
Sure. Yeah. The precision cleaning side of the business is really, contaminants can cause cross-contamination, corrosion, fractures, and we're testing a lot of and cleaning hydrogen tanks, oxygen and hydrogen lines. We do a post-bagging service. We do leak testing on a lot of this equipment as well with helium leak testing, mass spectrometry to verify that it can hold its pressures and we can quantify exactly how much it's leaking.
Outstanding. Yeah, thank you so much. As a quick reminder as well, we actually have a few of our business development directors on the chat also. So we also have a representation from Rebecca Thomas, who is our current business development director for our space customers. So feel free to reach out to her, and we can also provide information for her as well after the call. Just feel free to reach out. So really in regards to, as I was saying earlier, we support the end-to-end design journey for space vehicles, payloads, as well as launch vehicles. Through really comprehensive test programs, test planning, and of course, comprehensive complementary testing between materials, non-destructive testing, as well as product quality testing. So real quick, let's go ahead and kick over to Q&A. Thanks so much, Eric, for helping us out there. And of course, answering my questions, because I'm always a curious guy, especially when it comes to our services available for these applications. Let's open up the floor to our audience for any questions for our panel. And a quick reminder for everybody, we have an open Q&A. Feel free to type whatever questions you have into the box, and our panel will be sure to hand that off and answer as best they can. We'll go ahead and give it a minute or two.
Michael, if you don't mind, let's go back to that one previous slide because, it really shows our company and how we can support our customers' journey from the beginning stages of proof of concept to launch and everything between. I can see how PQT fits within the fabricate, integrate, and test stage, along with launch and orbiting simulations, and how NDT is instrumental in the other areas. I don't know if Frank, if you'd like to.
Yeah, I totally agree, Eric. I mean, if you look on the DT side, right? I mean, we're in the forefront of innovation and engineering. As new materials are coming online, we are doing testing on the chemistry, verifying the the chemical, and then after we verify all the new materials, then they move on to mechanical properties, right? That we can do all the other mechanical properties to verify that as well. And then it goes on to advanced testing like fatigue crack growth and fracture toughness. And then as you said, so after it becomes a component, our other areas then come into the testing like PQT and NDT to verify, fractures or, porous in NDT, as well as how the component behave in PQT.